Section 4.4 covers the basics of the multiplication rule. Unlike the addition rule where we had two events, A or B, and we wanted either of them to occur or both of them to occur in a single trial, when we're talking about the multiplication rule, we're now dealing with two separate trials. For example, we want event A to occur in the first trial, and then on a subsequent second trial, we want event B to occur. Just like we associated the word or with addition in the last section, we want to associate the word and with multiplication for this section. Example 2, we have this table that we've been working with in the past few sections, and it says we want to choose two of these subjects without replacement. Without replacement means that once we pick someone or something, we can't pick them again. Find the probability that the first person selected is a male and the second person selected is a female. Down at the bottom here, we see a note that says, if we're choosing without replacement, we need to make sure we adjust any probabilities as we move through the problem. What that means is, for example, when we choose a male, we want to choose one of these 115 subjects out of 192. Okay, but once we do that, we're no longer choosing from 192 subjects because we've taken one of the males out. There's only 191 people left. So for the second trial, now we're choosing of the 77 females out of 191 total people because that one male is gone from the first trial. That gives us our answer, 0.241. So what we had just found when we had selected the female second after already selecting the male first is called a conditional probability. Conditional probabilities are written like this: probability of B given A, and it represents the probability of event B occurring after event A has already occurred. Okay, going back to the last problem, we had chosen a female after we had already chosen a male. This notation right here is read B given A, and it means that event A has already occurred when we go to choose or find the probability of event B. If events are independent, okay, it doesn't matter. We don't have to adjust our probabilities at all. They don't have any effect on each other. But if they're dependent, like they were in the last problem, it means that the first event has an effect on the second one. So choosing a male first had an effect on choosing a female. Those were dependent events, which means we had to adjust the probability when we did our second trial. Okay, in certain problems, it doesn't affect it, like that first problem we did, the true-false multiple choice problems. Didn't matter if we got the true-false one right or wrong. The probability of selecting a correct answer in the multiple choice was still 1/5. Those would be independent events. Here's the actual definition of independent events. Two events are independent if the occurrence of one doesn't affect the probability of the occurrence of another. Okay, if we actually did the math, we would see that the conditional probability of B given A is the same as just the straight probability of event B. Two events are dependent if the occurrence of one affects the probability of the other. However, just keep in mind that it doesn't mean that one event is the cause of the other. Example 3, your friend claims to be a psychic. You shuffle a standard deck of 52 cards. You hand it to your friend. You ask him to pick the ace of spades. If he's successful, you take the deck, you reshuffle it, you ask him to pick the ace of spades a second time. First question, should this problem be completed with replacement or without replacement? Since we're putting the ace of spades back in the deck and we're reshuffling it, this problem is completed with replacement. Okay? Because of that, these two events are independent of one another. Right? The first event, there's a 1 out of 52 chance of him picking the ace of spades. Okay, moving on to the second event, we put that card back in, we reshuffle it, there's still a 1 out of 52 chance that he picks the ace of spades. Total probability, 0.00370. Example 4, we have a sample of 100 M&Ms, 22 of which are blue. Mr. Sager uses a graphing calculator to randomly select 2 M&Ms to eat. This is how I eat my M&Ms. Should this problem be completed with replacement or without replacement? Obviously, I can't eat the same M&M twice. If I want to choose 2 M&Ms to eat, I don't want to be able to pick that same M&M twice. So I pick the first one, I pick a second one after that first one's already been selected. This problem should be completed without replacement. Find the probability that both M&Ms that Mr. Sager eats are blue. So since we're doing this problem without replacement, these are dependent events. So to start, 22 out of 100 are blue. That's the probability that the first one will be blue. Once I pick that one, that's removed from the whole sample of M&Ms, and the probability that the next will be blue is now changing to 21 out of 99. Total probability 0.0467. Now, some problems are going to involve multiplying a number of different conditional probabilities together. For example, let's say you were asked to find the probability of Mr. Sager choosing 5 M&Ms, and what's the probability that all 5 of those would be blue. So we found the probability that the first 2 would be blue. The probability for the third M&M would now be 20 out of 98, continuing on from the last problem, and then 19 out of 97 for the fourth, 18 out of 96 for the fifth, etc. Okay, so we just keep changing the conditional probability of subsequent events. But let's say instead of 5, it was 20. Okay, at some point, we're going to say this is really going to be too long of a problem to have to change all of these fractions. It's too cumbersome. In other words, cumbersome means complicated or just it's too hard to do. So instead of treating these all as dependent events where we're changing the probabilities and making them conditional probabilities, we're going to treat them as independent. Okay, we can do this as long as our sample size is no more than 5% of the population. And keep in mind that this is really a shortcut. It's not really the correct way to do the problem. So the only reason that we would want to do this is because calculations are otherwise cumbersome. In other words, to do it the actual correct way would just be way too much work, and we're going to take this shortcut instead. So in other words, we're doing it to keep it simple. All that said, let's look at example 5. Here we have a batch of 100,000 heart pacemakers. 99,950 are good, 50 are defective. In part A, we want to choose 2 of them, selected without replacement. Find the probability that they're both good. This is easy enough to do the correct way. The probability that the first is good is 99,950 out of 100,000. We take that one pacemaker away. The probability of selecting another good one is 99,949 out of 99,999. Multiply them, we get our answer, 0.999. Part B, now we want to select 20. If 20 of those 100,000 pacemakers are randomly selected without replacement, find the probability that they are all good. So basically for this problem, to do it the quote-unquote right way, we have to keep changing our fraction. So the next one would be 99,948 out of 99,998, okay, and then on and on and on for 20 fractions. Okay, that would be very cumbersome. It would be a real pain. So instead of treating these as dependent, we're going to treat them as independent, okay, which means they all are considered this original probability, and we just keep that probability for all 20 of our selections. Okay, we raise that to the 20th power because we just keep that probability times itself 20 times. And that gives us our answer of 0.990.